Hello 8th graders, today you're going to be looking at the difference between ionic and covalent bonds. Last week we talked a little bit about ionic bonds and how ions are formed, but now we're going to bring it all together and talk about the multiple different ways that atoms can stick to each other or bond. Before you go forward with this video, please make sure that you have completed the Do Now at the top of your page, and then go ahead and start the video back up again. So if you're still watching, you've completed the Do Now, and we're going to go over a little bit of background information and a little bit of review before we get into the new stuff. So for some review. First thing that we got to talk about and remember is how protons and electrons pull on each other. So they have opposite charges, they pull just like a magnet. Opposites attract, plus attracted to minuses. And that's what keeps all the electrons buzzing around the nucleus. Otherwise they would go flying off forever, but they're attracted to the protons, so they stay around the protons. Well, that means that some atoms are better at this than others, so if you have more protons, or if you have fewer rings, we've talked about both of these possibilities, that means that you have a smaller atom, and that's kind of important for this unit because it's going to tell us how things bond in just a minute. So let's take three examples. Let's take lithium, beryllium, and sodium off of the periodic table and just make sure that we're clear on why things get smaller or bigger because of protons and rings. So let's start off with lithium, the one in the corner. And lithium has a very little magnet. So it has 3 protons on the periodic table, and that's not very many protons. So it doesn't pull very hard on its rings, and they're able to relax a little bit and stretch out. So lithium, even though it doesn't have very many things in it, takes up quite a bit of space because its electrons are allowed to spread out because of the small magnet in the middle. Well, if we go over one and we go over to beryllium, we've added a proton, so it's got a bit bigger of a magnet. Not a ton, but a little bit bigger. Because its magnet is bigger, it pulls on those rings more and kind of sucks them in a little bit. So beryllium is a smaller element, even though it has more things in it. Well, now that'll keep continuing as you go down the periodic table, so as you go to the right, things get smaller. Now let's talk about a column. If we go from lithium to sodium instead, sodium is quite a big element compared to lithium, even though it has a lot more protons. Sodium has 11 protons and lithium only has 3. So sodium's got quite a good magnet in the center of its atom. However, because it has that third ring, whereas lithium only had 2, that third ring makes it even harder for that magnet to grab onto its outer electrons. So that last one spreads out a lot. So as you go down a column, that's up and down, as you go down a column, things are going to get bigger as you go down because you're adding rings. The last thing we've got to talk about is small atoms are good at stealing. So they're good at stealing because they have very little space to steal from. So like, for example, beryllium, compared to lithium, beryllium doesn't have very far to reach for its magnet to grab onto something. Lithium has quite a big distance to reach, and sodium has an even greater distance to reach. So lithium and sodium are not as good at stealing as beryllium. And as you remember, as we go all the way over to the right side of the periodic table, fluorine is very collapsed. It's only got 2 rings, and it's got a fair amount of protons, and so it's very small, and it's able to grab onto other electrons and steal very well. So what this means for our periodic table is that on the left-hand side, we have the large atoms. So they're really big. That means that they're not very good at stealing, and they have these low electronegativities, which remember is how good at stealing they are. On the right side, where the nonmetals are, those are the smaller atoms, and they're much better at stealing, and it's because of their size. So if you work this out, the first column has 1 valence electron, so lithium, sodium, potassium are the metals in that first group, the alkali metals. They are not very good at stealing, so in order to obey the octet rule, they have to lose their 1 electron, and they turn into +1. And as you work all the way across the periodic table, you're going to see that the metals are going to make either +1s, +2s, the transition metals can make a range of ion, and then the boron group is going to be able to make +3s. Carbon, right in the middle, because it has 4 valence electrons, doesn't tend to make ions, so not applicable. Then we get over into metal country. We've got -3, -2, and -1 because nitrogen wants to steal 3 electrons. Oxygen in that group wants to steal 2, and the halogens want to steal 1, and they're very good at it. Please add these charge symbols to the top of your periodic table on your take one, because these numbers are going to be very useful for us as we predict what kinds of compounds get made, just like we did last week. Finally, the last one is the noble gases, and of course, they don't like to bond either. Before we go on your paper, I need you to respond to this quick right. Ionic bonds always happen between a metal and a nonmetal. In other words, if you were to take any of these -3, -2, or -1s, they really like to bond to the metals. Please explain why. If you want to think about this another way, how come metals don't steal from metals? Or how come nonmetals don't steal from nonmetals? Please pause the video while you write your answer. Now that you've written the answer to your quick right, let's talk about why that happens. So ionic bonds are because a metal and a nonmetal get into a fight, and the metal is not as strong at holding on to its electron. So in this little dog example that's running on your screen, the dog on the right is the nonmetal, and he's very easily able to steal the electron, or the bone in this case, from the metal. Now, once they steal from each other, they have opposite charges. So the pluses and the minuses, once they've stolen, they stick to each other, just like magnets do, and that's a compound. So sodium and chlorine, they stick together. That's table salt, sodium chloride. Covalent bonds. So the difference between an ionic and a covalent bond is not too tough. But it comes down to this question. What if two nonmetals were fighting over the same electron? Well, think of it this way. If two nonmetals were fighting over the same electrons, it'd be like these two dogs. So these are both chlorines. On the periodic table, on the electronegativity chart, chlorine has an electronegativity of 3. Well, if you have two evenly matched elements fighting over the same electrons, they're going to grab onto each other's electron and kind of get into a never-ending tug-of-war. And it's actually a really strong bond. So they stick together because they're each holding on to each other's electrons. So on your paper, covalent bonds always happen between two nonmetals. The reason is because they're strong enough to hold on to each other. A metal and a nonmetal, the nonmetal easily steals from the metal. That's ionic. This one's covalent because they both stick together. We can use Lewis dot diagrams to really show this well. So the two chlorines that are in the dog picture, here are their Lewis dot diagrams. I've used circles and X's to show the electrons for each individual chlorine. So here's what's going on. This chlorine has an opening. It wants 8 electrons, but it's short. It's only got 7. And it sees that extra one hanging off of its neighboring chlorine, and it grabs onto it because chlorine's a small atom. It doesn't have a very big radius, so it can reach out and grab things really well. Same with the other chlorine, though. So the one with the X's reaches out and grabs onto the circle, and what ends up happening is they end up holding onto each other's electron. Well, this isn't all bad, though, because if you look all around this chlorine with the circles, notice now that there are 8 electrons, and that's exactly what it wanted. So if you overlap this edge so that they kind of share each other's electrons, this chlorine on the left is happy. So is the one on the right because it's got the same thing going on. It's overlapping its electron shells and able to have 8 in its valence shell. So a quick check-in. These are the two strategies we've talked about in these just short couple of minutes. The one on the left is where sodium and chlorine get into a fight, chlorine steals. The one on the right is where two chlorines get into a fight and they both end up having to share. On your paper, I need you at the very bottom to write down in your words, not mine, in your words, how do these two strategies help the atoms to obey the octet rule? Please pause the video and answer that now. So hopefully now that you've answered that question on your paper, I can show you my answer to that and we can compare, and hopefully we're similar. So in ionic bonding, the electrons are stolen so that the metal's lower ring is exposed. So in the sodium, that outer electron gets taken away, so the second shell is exposed, and that one's full. So that obeys the octet rule. The octet rule is they want to have an outer ring that's full. Well, when that happens, chlorine takes it and puts it in his outer ring, and now his outer ring is full too. And so by stealing, both of them actually end up happy. For covalent, the valence shells are overlapped, like literally overlapped. They kind of like merge them together so that the valence shells are then sharing 2 electrons. One is being shared to the other for both atoms. And in this way, they're both able to have 8 electrons in their valence shell. So now we've got to talk about making some compounds. I'm going to do the first 2 on this, the next page for you. So if you're not already there, please turn your page to look at the same thing that you see on your screen. And we're going to be able to make compounds for any ionic or covalent compound at this point. So there are a couple of steps that I would like you to follow. The first step is to decide whether or not you're going to be making an ionic or a covalent bond. So basically see if they're metals or nonmetals. So if we have aluminum and chlorine that we're going to bond together, the aluminum is a metal and the chlorine is a nonmetal. So this is like the first example where we've got the weakling and the thief, and they're going to get into a fight and the thief is going to run off with them. So that's ionic bonding. Since this is ionic, we're going to draw our formula in the left box. So an aluminum, if you remember from when you put the pluses and minus above each column, aluminum is going to make a +3 and chlorine is going to make a -1. Well, if each chlorine can only steal 1 electron and aluminum wants to have 3 electrons stolen, it's going to take us 3 chlorines to satisfy aluminum so that everybody's happy. So we're going to get Al, one of them, so there's no subscript in chemistry if there's a 1, Cl, chlorine, with 3 of those. So the compound is AlCl3. Now let's say that we take our 2 chlorines. This is the one from the notes. So both chlorines are obviously nonmetals, and they're going to get into a tug of war with each other. And that's a covalent bond. So they're going to overlap each other's shells. This is not an ionic bond, so we don't have to put anything in this box. But for covalent, I want you to draw Lewis dot structures and show them merged together. For this box, I'd like you to either use different dots, like dots and X's like we did in the notes, or different colors, so maybe get some markers, because I want to see the different valence electrons for the different atoms, and it can get kind of confusing if you don't use something to show the difference. So for 2 chlorines, we've got our dots and our X's, and they've got an overlap in the middle, but everyone has 8 around them, and that's obeying the octet rule. For the remainder of your page, I need you to please pause the video and go ahead and attempt the rest of these. I'm going to, when you start the video back up again, I'll go through each one individually in case there are any that you're not sure about. If you want to scrub to the end of the video and see all the answers popped up on your screen and then maybe rewind it a little bit to see how I did some of the ones that might have been confusing or tough, please make sure you do that when you are finished. Okay, so now I'm going to go through each one of these examples on the back. Again, please scrub to the end. If there are any that are confusing for you as I go along, you can come back and rewind. So magnesium is a metal, and bromine is a non-metal. And so when these two things get together, they are definitely going to make an ionic bond. So when they make an ionic bond, magnesium is going to be 2+, so 2+, and bromine is going to be just a 1-. So in order to be able to steal all of the electrons that magnesium wants to have stolen, we're going to need 2 bromines. You always write the metal first, so we're going to have magnesium, we just need 1 of those, and then 2 bromines. For sodium and oxygen, sodium is a metal, oxygen is a non-metal. So what we're going to get, again, is an ionic bond. And now we've got to decide how many of each thing. So sodium is going to make a 1+, oxygen is going to make a 2-. So in order to satisfy oxygen, because oxygen wants 2 electrons, sodium, we're going to need 2 of you. So sodium, Na, 2, and then just 1 oxygen. For hydrogen and nitrogen, hydrogen is a nonmetal, and so it lives with the metals, but it behaves, it's very unique. It behaves in its own way, but it is a nonmetal, and so is nitrogen. So when hydrogen and nitrogen get together, now we're going to have a covalent. And so for this one, we're going to need to do Lewis dots. So I'm going to start off with my nitrogen. So I'm going to start with my nitrogen up like this. And nitrogen has 5 valence electrons. So 3, 4, 5. Now I'm going to switch colors to do my hydrogens. So hydrogen only has the 1 valence electron, but notice that there are like 3 little parking spaces around this nitrogen now. So I can put 1 hydrogen there, 1 hydrogen there, and 1 hydrogen here. And remember, hydrogen wants to be just like helium. So if it has 2 valence electrons around him, he's going to be satisfied, and that's what we've got for each of the hydrogens. And of course, nitrogen now has 8 around him. And if you were to write this like a compound, and I didn't ask you to, but if you were to, you would write NH3, just like that. Now we've got calcium and phosphorus. Calcium is a metal. Phosphorus is a nonmetal. And so we're going to have another covalent. And so we've got to make some Lewis dots again. So this one's going to be a little bit different than the hydrogen-nitrogen one. Oops, I apologize, this is not covalent. This is definitely going to be an ionic bond. So sorry about that. Let me erase this. Start over. This is definitely going to be ionic bond. So for an ionic bond with calcium and phosphorus, calcium is going to make a 2+, phosphorus wants to make a 3-. So this one's a little bit tough at first because the 3 and the 2 don't go together with 1 and 1. So you can't have just one calcium and one phosphorus. So what it ends up needing is if you increase each one at a time, so like I obviously need more pluses, but if I have 2 calciums, that's not going to be quite enough. And then you're going to have to figure out how much of each thing. When you're done, you'll figure out that you need 3 calciums and 2 phosphoruses in order to make this thing work out. So if each calcium brings with it 2 pluses, if you think about that, that brought with it 6 plus charge, and the phosphorus, since we have 2 of them and each one brought 3 minuses, that brought with it 6 minus charges, and then those two things can cancel each other out, and they're happy that way. So we keep going. Now we go to potassium and chlorine. For potassium, we have another metal. Oops. For chlorine, we have another nonmetal. And so with a metal and nonmetal, we are going to have an ionic bond. And if we're having an ionic bond, we need to figure out charges first. So potassium is going to make a +1, chlorine is going to make a -1, and those things work out great together. So KCl is the simple compound. Lithium and chlorine. Lithium is a metal. Chlorine is a nonmetal still. Now we have a metal-nonmetal, still ionic. And for ionic bonds, we need charges. Lithium is going to make a +1. Calcium is a -1. Again, those things go together great. So LiCl is our compound, lithium chloride. Now we have 2 bromines. Bromine is a nonmetal. So that is going to make a covalent bond. For a covalent bond, we're of course going to do Lewis dots. So I'm going to make the first bromine in red. So bromine is in the 7th column, and that means that it has 7 valence electrons. If I can get them in there. 2, 3, 4. Okay, there's 7. For my other bromine, I'm going to use blue. And it also has 7 valence electrons. And these 2 in the middle are the ones that are going to overlap so that both bromines have 8. For hydrogen, hydrogen is a nonmetal. Fluorine is also a nonmetal. So we're going to have a covalent bond. You'll learn in high school that fluorine pulls way harder than hydrogen. So this is going to be called a polar covalent bond, but you'll figure that out in high school very soon. So we're going to go over to the Lewis dots again. Hydrogen, remember, only has the 1 valence electron, so it gets 1 dot. Fluorine has 7, so 1, 2, 3, 4, 5, 6, and 7. And now fluorine has 8 dots around him. Hydrogen, remember, only wants 2 to be just like helium, and he is happy as well. All right, for your closure, what I need for you to please do is study these 2 animations. So in the 2 animations that you saw in this video where we had ionic bonding and we had covalent bonding, I used these 2 dog pictures. Obviously, analogies are not perfect, and so I want you to, for your closure in the last spot on your paper, please write down, based on what you've learned about ionic bonding, what is one thing that isn't quite accurate or what could have been improved about this analogy to make it closer to the real story of ions. Same thing for covalent bonding. What could have made this example better in order to make it a better analogy?